You are listening to EE Times On Air, and this is EE Times Current. I'm Eric Singer. Welcome to Brains and Machines, a deep dive into neuromorphic engineering and biologically inspired technology. In this episode, Dr. Elisa Donati talks about using neuromorphic circuits to integrate electronics with the nervous system. Your hosts are Dr. Sunny Baines of University College London and Dr. Giulia D'Angelo of Fortis in Munich.
Welcome to Brains and Machines. I am Giulia D'Angelo.
And I'm Sunny Baines.
In today's episode, Sunny will be talking with Dr. Elisa Donati, a researcher at the Institute for Neuroinformatics in Zurich. After the interview, we will be talking to Ralph Etienne Cummings from Johns Hopkins University about the issues raised.
Thanks, Giulia. Elisa is interested in biomedical uses for neuromorphic engineering, particularly providing an interface between electronics and the body. In this interview, we'll hear her discuss different kinds of interactions that are possible through the nervous system, why spiking networks may be more compatible with biological systems than their conventional counterparts, and a little about the trade-off between network size and neuron complexity. There are links to her work and some of the specific papers we'll be discussing on our website. You can check them out at brainsandmachines.net. Elisa and I first had a discussion at her office in Switzerland and then recorded this interview online. Elisa Donati, welcome to Brains and Machines. Can I start by asking you to tell me a little bit about your technical background and how you got involved with neuromorphic engineering?
Sure. First of all, thank you for having me as part of this podcast. It's something that I think is going to be fun. So my background actually is quite interesting because I don't have a classical background for neuromorphic engineering. So I have a bachelor and master degree in biomedical engineering. I was working on building front ends for measurements, but nothing invasive, nothing connected to the nervous system. And then I did my PhD in pure robotics. So building robots and building underwater robots. So it's something that is really different from what I'm doing now. And during my last year of PhD, I met Giacomo Indiveri. So then I started to see the possibility of expanding this robotics to neuromorphic computing and neuromorphic technologies. So then I started to work with him for the last year of my PhD. And while I was working with robotics, I realized that I was more interested in working with medical application. So I was studying these silicon neurons and synapses, and I realized that we can actually use neurons and synapses to interface with the body, so with the nervous system. So that's the reason why I started to work on this field.
So tell us more about these biomedical applications. What in particular are you working on? And what's your vision of what you'd like to achieve?
If I summarize what I'm doing with, let's say, one sentence, I would say that I'm interested in working on a closed-loop system and using neuromorphic technologies as a tool for working for these closed-loop systems. So in particular, I'm interested in interfaces with the nervous system, but with the peripheral nervous system. And I know that most of the research, and not only in neuromorphic community, even more in biomedical research in general, is more related to the brain, right? But I think that I'm interested in working with the peripheral system because I think that is, let me say, easiest way to access the nervous system, in a sense that already working with the peripheral one, we can already understand a lot and we can already achieve some really interesting results.
So what you're talking about is interfacing with the brain or interfacing with the peripheral nervous system. So I guess anyone would realize that putting a chip in your brain is going to be pretty invasive, whereas being able to, through electrical systems, to be able to input some kind of signal into your nerves would be much more straightforward, much less invasive, much less in need of regulation also.
What I want to do is exactly the idea of interfacing with the peripheral system to send signals using the peripheral system to get to the brain, right? I'm not sure it's less regulation. I mean, I think it's still problematic and I feel that it's still invasive. What I believe is that it's not so dangerous working directly with the brain, right? Probably it's not something nice to say, but in case of failure with the peripheral system, you can provoke maybe some pain, or maybe you can actually not having the results you were expecting, but it's not something really dangerous for the patient, for the subject.
So tell us a little bit more about how neuromorphic fits into this work on the peripheral nervous system.
So the reason why I decided to work with neuromorphic rather than classic biomedical approaches is because I believe that if you have a system that shares some similar characteristics with the system you want to interface with, you can have a much natural and much better interface, in this case with the nervous system, right? So if I'm able to build something that uses the same time constants, the same principle of communication that we have in the nervous system, I believe that this interface is going to be more successful. Like having two systems that they actually speak the same language with even the same speed, if you want, same time constant. That is something that makes the use of neuromorphic technology promising, right? So it's really having two systems that they have similar aspects, so you can improve this interface.
So the process is that you would analyze the way the peripheral nervous system responds, and then you would build a neuromorphic system to be able to feed it correctly encoded information so that it could most easily accept what you're feeding in. Is that right?
Yeah, exactly. So this is something that comes natural when you work with neuromorphic technology. So if you are able to produce a signal that is in the correct domain by looking at neuroscience, and if you're able to reproduce it by using neuromorphic technologies, this is something that I believe that is going to improve the communication with the nervous system.
Very good. So give me an idea of what kind of applications you're thinking about. What springs to mind for me are prosthetics, but I'm sure there are more things that you have in mind.
I think definitely that is interesting with the peripheral system, right? So in the case of the prosthetic devices, it can be valid in the moment you want to send some feedback to the patient. So you want to encode some information, and this information can be some mechanical information like mechanoreceptors output, temperature, even pain in principle is something that you can encode and you can send to the peripheral system, but it's also valid for not only the peripheral system like the welfare cessation, but it's also for the autonomic one, right? So for example, there are many studies about this vagus nerve stimulation. So the idea of stimulating the vagus nerve to produce some particular behavior, like starting with something that is classic heart pacing. That is also something I was working recently. So generating the correct discharge of the vagus nerve to have the desired heart activation. But it can be also, for example, there are some kind of diabetes that still have the insulin, but they are not producing correctly. So there are some new studies where you can actually use stimulation of the vagus nerve to generate the correct stimulation and generation of insulin. So this is, for example, another application where the closed loop is really important, right? If you want to release the insulin, you need to know your actual concentration of glucose. So you need to continuously close the loop. And this is another example where I think this approach can be successful.
That's really interesting. So I guess what we should do is we should understand a little bit more about the actual circuits you're building, because essentially you're working as a chip designer in this circumstance, right? That's your interest. So what are these neuromorphic circuits that you're building? What do they look like? What are their characteristics? Tell us about them.
So yes, I actually design my own chip. So I'm not the chip designer, but I design chip. And in particular, the goal is to try to design like neurons, for example, that are very similar to the biological one. So there is something that is probably not the mainstream or the trend that we have now in classic neuromorphic computing. So what I do is I try to have these neurons. For example, I'm working with Hodgkin and axonal neurons, and I even try to have more degree of freedom in these neurons because I have multiple ionic channels. And in particular, in my neuron, I even try to have independence in these ionic channels. So I can actually have different behavior. So to try to have even more dynamics and similar to the one of the nervous system. Because the idea is to try to increase the similarity to improve the communication between the silicon and the natural neurons. So at the level of synapses I'm now working, I don't need big chips with multiple neurons and thousands of neurons. I need few neurons, I like 32, 64, because the idea is not the one of building complex networks, but rather to have similarities and try to use simple neurons already for doing computation.
What I think is interesting about this application is that essentially you're trying to mimic biological systems, but not because you want to do biology, which is what some neuroscientists do, but you actually have a technological purpose in mimicking biology, which is a sort of interesting twist on neuromorphic engineering, I think.
Yeah, it's actually true. It's actually true. I'm using what they're doing, right? So I need to know how a neuron works to actually reproduce it in silicon, right? I need to know the neuroscience of neuron. But the idea, I have a purpose, right? I want to build them because I want to apply them. So I want to use them to communicate with the body. But I also think that at the same time, you can use what I'm building as a validation tool, right? Because you can prove, you can test your hypothesis in something that is actually built in silicon. So I think probably what I'm doing has this double purpose, right? So on one side, I want to build something, but I can also use what I'm building to test hypotheses.
So what's the next step? So you're working on a chip at the moment, or are you already in the testing phase?
So at the moment, I'm designing a new chip. So the idea is to try to use neurons as receptors. So try to understand which is the best way to send input to the neurons for this communication. I still don't know how to interface with the nervous system by using neuromorphic technologies. So I'm still at the phase where I need to understand the best way of sending signals to my chip rather than understanding the dimension of the number of neurons I need, how to connect them. So while I understand, I design new chips, and then I use them to basically have a closed loop to try to understand, and then I change my design and try to close the loop at this level of design.
And give us some idea of the features of these designs. You've said it's a Hodgkin-Huxley model. So is it running address event representation? Is it analog? Is it digital? Tell us a little bit about how you implement these neurons in a circuit design.
So the neuron I'm designing is inspired by the model of Misha Mawald. It's a famous neuron, probably the first silicon neuron. I modified this design because I want to have a higher similarities. So I have this possibility, as I was saying before, of controlling individually the ionic channel and have different behaviors. So it's not exactly the same, but it's based on the Misha Mawald model. At the moment, the chip I have is analog, so I design mixed signals chip. So in particular, I have this core that is analog, where I have my neurons and synapses, and the way I interface with the neuron is based on the address event representations. But what I'm trying to do now, for example, I would like to try to bypass this digital part and build in receptors. Try to use the neurons and sending directly the input, inject directly the input to the neuron, bypassing the spike, the digital part, and try to use this continuous input to modulate the behavior of my neuron. So it's like, rather than more cortical neurons, more having receptors.
Can you go deeper into that from an electronic point of view? What would that look like?
So from the electronic point of view, what I need to do is like an interface, right? So I need to send the input to my neuron, but since I work in subthreshold domain, I work in analog domain, I need to have an interface to regulate my input to be in the correct range. If I take like a standard sensors for measuring temperature, any kind of signal, and I want to inject in my neuron, if it's to like order of microamps or milliamps, this is definitely not a kind of current that I can inject in my neuron, right? So I need to be sure that this current is in the correct range. So what I'm doing now, I'm kind of designing an interface with the neuron to be sure that the range is the correct one. But the neuron itself is the same. So I have like some biases where I can go in the regime I want for my neuron, and then I'm going to send this current as an input to modulate the excitability of the neuron and to have some particular behavior.
So what are the next steps after that? So once you feel like you understand what the behavior of these neurons is going to be and that it's well matched to the peripheral nervous system, do you have partners within your university or elsewhere who you might work with to do experiments in, I don't know, animals or people?
I have partners. So this idea is, I have many collaboration, and in particular, I have collaboration with group of neurorobotics where they have basically access to the technology, and actually even with clinics where the clinician can actually do the experiment with patients. So what I do now, I collaborate with them to find the right regime of my neurons to have the possibility, for example, the firing rate I need to send the stimulation to the nerves, the number of outputs they require. So I work with them to have the constraints on my system. And once I have this new chip, the idea is to try to understand how to scale up, because I cannot do much with a single neuron. But I can definitely try to understand how many of those neurons I need, the constraints of the neuron, the parameters of neurons that they need to have to be able to use in real experiment with humans, actually. And at the same time, I would also try to understand how to use these neurons to generate output that we can use directly in closed loop stimulation, for example. But this is a long-term plan.
And I understand that some groups are using something called TENS to do that stimulation. Can you talk a little bit about that and how your neuron, if you're using that indeed, how your neuron might modulate the TENS signal?
So the TENS is a way to stimulate the subject or the patient, but it's totally not invasive. So it's something that you don't need to have any regulations. So it's something that you can even use in your lab to do some preliminary results. So when you do this kind of superficial or non-invasive stimulation, of course, you can stimulate, you can see how the subject patient react to this particular stimulation, but it's not something that is really interfacing with the nervous system, right? Because it's something that you have at the superficial level, so you have at the skin level. So if you think of sending like a train of spikes to the skin, you probably are able to elicit something, but it's not something like in the natural way, because in the natural way, it's something that comes at the level of nerves. So in principle, my long-term goal is to have invasive stimulation, right? So the idea is to really work on real implants inside the nerves to send the stimulation. And the idea of how to use my neurons is slightly different, right? But the principle is similar. So the idea is to send stimulus in the natural way, so by regulating, by changing the frequency. Because at the moment, if you look at the stimulation that you have, they can be in amplitude, in frequency. But if you think of the nervous system, the stimulation is always in frequency. It's not in amplitude. You always regulate the frequency. And this is something that you can do with a chip, right? So if you have a neuron and your neuron is firing, so if you think of the firing like a train of spikes, you can actually use it to send it directly for the stimulation. The way you use for non-invasive, like TENS, and the way you use for invasive is slightly different, because you probably have a different dimension of the stimulation. Because once you are invasive, you need to send a short amount of current, and you need to send these biphasic signals because you want to have a discharge of the nerve after every time you send like a pulse. And this is something that you don't have, for example, in external stimulation. Because in external stimulation, you actually have to send something probably longer, because you need to think of the skin, and the signal needs to pass through the skin. So you need to send like more reliable signal. So the stimulation is not exactly the same, but starting from the neuron output, you can modulate it to get both the non-invasive and invasive. The natural way is to go for the invasive. Unfortunately, it's not the easiest way. So you need to go with implants, and you have a lot of rules. And so it's not so easy. So we can start with TENS, so superficial, and then maybe in future move to something more invasive.
Can you say something about the difficulty trying to channel lots of information from something complicated like a hand down the limited bandwidth that is 1 or 2 or 3 nerves going through your arm.
So when you have multiple sensors of your hand and not a single one, then you need to understand the way of combining all these sensors in a spike trade or in a stimulation to send to the patient, right? Because, for example, if you have 100 sensors, you're going to send 100 signals to the patient. The patient doesn't understand what you're sending. And even if you go in invasive, you have to think that the current probe, the current electrodes, they have few channels, like 10 channels, 20 channels. So you need to combine these multiple sensors in few. So this is another huge part of the research. So we need to understand how compress this information that is a temporal, because you have spikes, and the spatial information is something that is smaller. So we need to understand how to move from the higher dimensional space to the lower dimensional space to send something that is valid for the patient or the subject, and allow the subject and patient to understand some information from the sensors. This is another huge open area. It's something that I plan to work in the future because it's not clear how to compress this information, and it's part of my research.
Elisa Donati, thanks for coming on to Brains and Machines.
Yeah, thank you very much for these opportunities. It was fun, and I was really happy to be able to talk about my research.
Thanks, Sunny. I was waiting to listen to this episode. And for more about Elisa's work, please go to brainsandmachines.net. Now, we welcome back our regular commentator, Professor Ralph Etienne Cummings from Johns Hopkins University.
Good afternoon, ladies. Good to see you again. Looking forward to a nice discussion.
Hi, Ralph, and hi, Sunny. So, Elisa has a huge journey behind her back, and it's pretty unique. So, Elisa has a PhD in biorobotics from the Institute of Biorobotics, the School of Advanced Studies in Pisa. And she worked a lot on the Lamprey central pattern generator. I think she mentioned once, just talking between me and her, and she used then neuromorphic electronic circuits interfacing to the robotic actuators for this biomimetic robotic lamprey, which I think it came out with a nice publication with Giacomo Indiveri, a spiking implementation of the lamprey central pattern generator. So all of this, because it's not mentioned in the interview, and I'd like to talk a little bit about the CPG, so the central pattern generator. So basically the CPG works everywhere we need to produce a rhythm motor patterns, right? So my question is, do we have other example of neuromorphic CPG systems as she has done for the lamprey?
Yes, there are quite a few, in fact. So the person that started looking at the biology of lampreys basically is, Avis Cohen and Sten Groner out of Sweden, where they started basically looking at the structure of the spinal cord and understanding the various neurons in the spinal cord, how they play a role in terms of guiding the swimming action of the lamprey. From there, two things happened. Ranu Young, who was, I think, Avis's postdoc, was one of the people who really kind of put CPG neuromorphic systems on the map. But at the same time, Steve DeWerth at Georgia Tech essentially had deep interest in this area as well. And he did build the first lamprey model that was embodied in a fictive swimming contraption that essentially contained like a model of a full lamprey with motors and everything. And then they had a distributed network of neurons that implemented the different segments. And he demonstrated the swimming action of a lamprey. So that was kind of the more, can I mimic the activity of a lamprey and can I make that drive a robot? I think in his case, it was not, a free-moving robot. It was very fictive swimming, meaning that the robot was contained and the action happened.
Can I just say that Avis Cohen is from the University of Maryland?
Yes, that's correct. She's retired now, but that's where she was. But then afterwards, a few of us, including myself, got involved with understanding the lamprey spinal cord from a perspective of trying to understand human spinal cords, right? And then can we make prosthetic devices that would then essentially mimics of the spinal cord that would restore locomotion, restore function in a dysfunctional spinal cord. And that led to a lot of work that came afterwards in cats, in lamprey themselves, of course, and ultimately came the work of what we did with Vivian Mushawar on restoring walking in a paralyzed cat, and so on and so forth. So yeah, so there is a long history of building lamprey-based, CPG-based control for walking robots. I must say one other person actually who came out of the Zurich lab, Susanna Still. And if you remember reading anything about her, but she was interested in locomotion, not necessarily from lamprey, but more from insects. But she used lamprey ideas in terms of generating the control patterns that would then go to the different limbs of the walking robot. And I think she was doing like 6 legs and so on. It'd be interesting. I don't know what happened to her actually, because she left the neuromorphic community, but it'd be interesting to track her down and see what she's up to these days.
Did you mention Alki Eisbert?
Oh, so Alki came later after, the lamprey. Alki's worked with salamander, if I understand correctly, and he basically looked at the different changes of gait from a salamander in water versus a salamander on land, and how that transition happens. So yeah, so that came a little bit later after we started getting more into how do you deal with lamprey control under different conditions of the surface upon which that animal is operating, right? So in water is very different from underground. And how do you make that transition? And also, I should also point out Tony Lewis was one of the starting individuals as well that worked on this. This is what the work he did with George Perky at USC, where they basically used learning to reconfigure the networks of the type of connectivity that give rise to certain swimming characteristics, with CPGs. So anyway, just to finish the thought, there's quite a deep level of publication in this area.
Tony Lewis, who's now at BrainChip.
Yeah, I think he's a CTO, a newly appointed CTO of BrainChip.
Yeah, I'm hoping to go and visit him before or after NICE in
Excellent.
April.
And I think they just little aside, BrainChip just put out their new system. It's available for $800 purchase.
Oh, wow.
I was like, maybe I'll contact Tony and say, hey, can I get one? Yeah, Tony and I have published together quite a bit as well. So we have a long history together as well.
I know that there is another great scientist in Denmark, Max Stromer, that is working with the CPG, but for exopods. But I wanted to know more. So this clarification just for myself, she talked a lot about the peripheral nervous system. And I just want to clarify for everyone that we know that the peripheral nervous system carry on motor commands from the central nervous system to the body muscles. So the central nervous system is responsible for processing and integrating sensory information. So first of all, I loved her bioengineering point of view because it brings me back to my biomedical engineering bachelor. So I really love the fact that she's thinking about patients. She's really thinking about human beings. And this is really interesting for me. And she also pointed out, I want to just use her words. I believe that if you have a system that shares some similar characteristics with the system you want to interface with, which is us, you can have much natural and much better interface. So, of course, I'm a bit biased. This is, to me, the killer app of neuromorphic systems, and to me, it's the future. But then I have a question. How do we handle the complexity that comes to direct connection with the body, right? So she mentioned the pain. That, for example, is the most primitive sense. And I think it could be a good starting point, for example. Do we have any successful story of emulating pain, bio-inspired or neuromorphic? And the second question is, how do we handle this complexity?
Pain itself, I don't know of a neuromorphic system that deals with it. But Sunny, you had.
Yeah. So when Nitish Thakkar's group won the Mahawald Prize a couple of years ago, I wrote a story about that project. And one of the things that they specifically work on are what are called nociceptors, so pain receptors within a skin. And of course, the point of that is that they should send a signal whenever anything is happening that could be dangerous to the robot, that could actually rip the skin of the robot or something like that. So, of course, the question of pain is very complex because what pain means to a machine and what pain means to a human are very, very different. And I don't know what the ethics are of creating a pain pathway or using a pain pathway that isn't being used otherwise in order to improve the behavior, for instance, of a prosthetic or the usability of a prosthetic. I don't know how that would work in real life. So I would say that there are two aspects to the pain. One is how it's received by the human, and the other is how it's detected. And you would have to have some way of detecting it, but you might want to send it through a different pathway in case it went wrong and was just sending overwhelming pain signals for no reason.
So one thing that we know that at least in stepping, right, that usually we think of pain as being, I put my hand on the hot plate and that reaction, yeah. But well, firstly, the pain reaction loop is actually slower than what one might expect, which is kind of weird, right? You would think that, oh my God, you put it away as fast as you can. Second thing,